and the cooking pan. I used to boil lobsters in there. It's a large pan. The cooking pan I'm going to charge up, and the cooking pan here has a radius, whatever it is, maybe 20 centimeters, but look here at the handle, how very small this radius is. So I'm going to put charge on there, and I'm going to convince you that I can scoop off more charge here where the radius is small than I can scoop off here. I have here a small flat spoon, and I'm going to put the spoon here on the surface here and on the surface there, and we're going to see from where we can scoop off the most charge. Still charge from the previous lecture. So here we see the electroscope that we have seen before. I'm going to charge this cooking pan with my favorite technique, which is the electrophorus. So we have the cat fur and we have the glass plate. I'm going to rub this first with the cat fur, put it on, put my finger on, get a little shock, charge up the pan, put my finger on, get another shock, charge up the pen, and another one, charge up the pen, make sure that I get enough charge on there, rub the glass again, put it on top, put my finger on, charge, once more, and once more. Let's assume we have enough charge on there now. Here is my little spoon. I touch here the outside here of the can, of the pan, and go to the electroscope, and you see a little charge. It's very clear. What I want to show you now, it's very qualitative, is that when I touch here the handle, it's a very small radius that I can take off more charge. There we go. Substantially more. That's all I wanted to show you. So you've seen now in front of your own eyes for the first time that even though this is a conductor, that means that it is an equipotential, that the surface charge density right here is higher than the surface charge density here. Only if it is a sphere, of course, for spherical symmetry reasons, will the charge be uniformly distributed. If the electric field becomes too high, we get what we call electric breakdown. We get a discharge into the air, and the reason for that is actually quite simple. If I have an electron here, and this is an electric field, the electron will start to accelerate in this direction. The electron will collide with nitrogen and oxygen molecules in the air, and if the electron has enough kinetic energy to ionize that molecule, then one electron will become two electrons, the original electron plus the electron from the ion. And if these now start to accelerate in this electric field, and if they collide with the molecules, and if they make an ion, then each one will become two electrons, and so you get an avalanche. And this avalanche is an electric breakdown, and you get a spark. When the ions that are formed become neutral again, they produce light. And that's what you see. That's the light that you see in the spark. And so sparks will occur typically at sharp points, at areas where the curvature is strong, whereby the radius is very small. That's why the electric fields are the highest. How strong should the electric field be? Well, we can make a back-on-the-envelope calculation. If you take air of 1 atmosphere, dry air, at room temperature, then the electron, on average, will have to travel about 1 micron, which is 10 to the minus 6 meters, between the collisions with the molecules. It's just a given. On average, sometimes a little more, sometimes a little less, because it's a random process, of course. To ionize nitrogen, to ionize oxygen, takes energy. To ionize an oxygen molecule takes 12.5 electron volts, and to ionize nitrogen takes about 15 electron volts. What is an electron volt? Well, an electron volt is a teeny weeny little amount of energy. It's 1.6 times 10 to the minus 19 joules. Electron volt is actually a very nice unit of energy. Because once you have an electron and it moves over a potential difference of 1 volt, it gains in kinetic energy. That's the definition of an electron volt. It gains 1 electron volt. It's the charge of the electron, which is 1.6 times 10 to the minus 19 Coulomb, multiplied by 1 volt. And that gives you then the energy, 1 electron volt. And so, what it means then, let's assume that this number is 10 electron volt. We only want a back on the envelope calculation. So we want the electron to move over a potential difference delta V, which is roughly 10 volts, and we want it to do that over a distance delta x, which is 10 to the minus 6 meters. That's your 1 micron. And if that happens, you'll get this enough kinetic energy in the electron to cause an ion. So what electric field is required for that? That is delta V, the potential difference, divided by the delta x. So that is 10 divided by 10 to the minus 6. So that's about 10 to the 7 volts per meter. That's a very strong electric field. In reality, when we measure the electric fields near breakdown, it is more like 3 million volts per meter. But it's still very close. This was only a back on the envelope calculation. So very roughly at 1 atmosphere air, room temperature, when the air is dry, we get electric breakdown at about 3 million volts per meter. When the ions neutralize, you see light. That's why sparks can be seen. They heat the air. They produce a little pressure wave, so you can also hear noise. If you had 2 parallel plates, and you would bring those plates closely together, and suppose they had a potential difference of 300 volts, then you would reach an electric field of 3 million volts per meter when the distance d is about 1/10 of a millimeter. So that's when you expect spontaneous discharge between these 2 plates. In practice, however, it probably will happen when the plates are further apart than 1/10 of a millimeter. And the reason for that is that there's no such thing as perfect plates. The plates have imperfections. That means there are always areas on the plate which are not flat, but are a little bit like what you see there. Small radius. And that's, of course, where the electric field then will be larger, and that's where the discharge will occur first. However, if you touch the door knob and you get a spark, you feel a spark, and you look at the spark and you see that when you're 3 millimeters away from the doorknob that the spark develops, you can pretty sure that the potential difference between you and the door was of the order of 10,000 volts, several thousand volts at least, because over 3 millimeters it requires 10,000 volts to get to 3 million volts per meter. When you comb your hair, or when you take your shirt off, you get little sparks. You can hear them, and if it's dark you can see them, and you can be sure that at the sharp ends of this hair, of the fabric, that you have developed electric fields of the order of 3 million volts per meter, and then you get the automatic breakdown. Now, of course, high voltage alone doesn't necessarily kill you. What matters is not so much the voltage to get killed, but it's the current that goes through you. And current is charge per unit time. And so in SI units, it would be coulombs per second, for which we write a capital A, which stands for Ampere, the man who did a tremendous amount of research in this area, Frenchman.